So thanks everyone for being attending the first Open Planetary Lunch Talk. We're kind of figuring it out, as everyone is right now. We're gonna keep doing these every week on Tuesdays, at least as long as the current global situation happens, so we can hear another human's voice once in a while and maybe learn something that helps us with our work. So the first speaker is Michael St. Clair. He's the Chief Technology Officer of Million Concepts, which is my company. He's my business partner. He'll be talking about some data that we just restored for Matthew Siegler, Apollo heat flow experiment data from Apollo 15 and 17. It had some issues that he corrected. He'll explain those. And then we prepared it for the PDS under PDS 4. I think it's one of the first data sets to be prepared for PDS 4, so he has some thoughts about how to make that smoother now that more people are going to be expected to do that. So with that, I will mute and unmute Michael. If I can figure out how computers work. Unmute.
Hello, hello.
Michael?
Am I audible?
I can hear you.
Wonderful.
Yeah.
Okay, so yeah, like Chase said, I'm going to talk about these new reduced sets we made that correct, concatenate, and generally improve the accessibility of the Apollo 15 and 17 heat flow experiment data. I'll just call this the HFE data from now on. And I'm going to talk a little bit about our archival choices and a little bit about my experiences working with the PDS-4 format, including some tips and tricks. So this is obviously old data, but interest in it has been increasing over the past 15 years for several reasons. Maybe the main one is that it is increasingly accessible. You know, people are more interested in data if they can, look at it. None of it was available in standard data formats until 2005, when a team at the NSSDC transcribed it from a custom file system on magnetic tape. And then much more recently, just over the past couple of years, a group led by Seiichi Nagihara has recovered additional data that adds significantly to this record. Some of that data they've released in the PDS, and some of it is still only available in data releases alongside journal articles. So other reasons that people have been continuing to be interested in this, obviously people are becoming more interested in returning to the moon. And there are many, many more orbital data sets that offer opportunities for data fusion. But really the bottom line is that the HFE data is the only ground truth data for heat flow in the lunar regolith. And it is still not that well understood. And there are some features of the data that have been perennially confusing to investigators, particularly a gradual rise in temperature over time in all subsurface thermometers after correction for diurnal, seasonal, and precessional cycles. So the reduction in archival work I'm describing here is a component of a solar system working project, PI Matthew Siegler, and the grant's primary scope of work is using a novel thermal model to investigate some of those issues. And I'm specifically not talking about that modeling work in detail here, but suffice it to say that a couple of the numerical errors we found had to be corrected in order to effectively constrain parts of that model. And we decided that archiving a fully corrected, concatenated, and improved version of all available reduced HFE data would be very valuable for the community. Our primary goals in this archival project were correctness, usability, and clarity. So when I say correctness, I mean that, as I referred to, there are some errors in what we call the Lamont data, the data archived by the original instrument team, that we chose to correct, or managed, I should say, to correct in this. And the most persistent and horrible of these is something that we refer to as the bit flip. I think Kent Hills coined this term back in the early 2000s. So the red curve here is the difference between two sides of a Wheatstone bridge, a differential thermometer pair. And you can see that it takes on this horrible, jaggedy, completely unphysical pattern. And this is the case for all negative DT values in the entirety of the Lamont data. So in other words, anytime the top thermometer of a pair is warmer than the bottom thermometer of a pair, this happens. The error is not found in the data that Nagihara recovered, and the error is not found in the publications of the original instrument team. So we think that something went wrong in the instrument team's archival process. And our guess is that something funny happened in conversion between standard and exponential binary form when they were trying to translate their internal data to IBM 1130 floating point format. Because what this error does basically is confuses a relationship between mantissa and exponent. So like if you look at any of these red values, they've essentially taken, if the correct value was maybe negative 2 to the n plus a, the error translates that to the negative of 2 to the n minus a. So you have this rollover effect that you hit at the negatives of powers of 2. And this is correctable by sort of like manually and tediously curve fitting, but it requires a lot of effort. So that's one of the errors I'm referring to that we corrected. As this might suggest, the presence of this error in archival, the AHFE data has it's a very interesting history in and of itself and is an entire object lesson in data stewardship, but I'm not going to go into that in great detail here. For a more exhaustive rundown of that, you can take a look at our primary documentation in the bundle, our forthcoming article in Planetary and Space Science, or some of Seiichi Nagihara's publications. Okay, so past correctness, I wanted to talk about usability. So broadly speaking, we feel like usability is under-prioritized in data archival. Anecdotally, over half of investigator hours devoted to data analysis are spent on scientifically completely trivial tasks: data ingestion, cleaning, unit conversion, concatenation, etc. This is obviously to some extent unavoidable, but we're kind of enthusiastic about reducing this repeated and fundamentally wasted effort to maximize return on science. So we wanted to produce sets that were as close to off-the-shelf ready as we could make them for likely use cases. So what did this mean? This included concatenating different sets in the existing data record. So like the Nagihara data is really high quality, but it's formatted quite differently from the Lamont/PDS3 data. So we put them in the same format and in our later sets in the same time series. Other things, pruning impulsive outliers, correcting the numerical errors, standardizing units. The Lamont data use these really weird time units, computing explicit temperature values at each thermometer rather than differential plus average values, and even computing explicit temperature values at each depth for a particular site for these kind of maximally frictionless incorporations of this data into the workflows of new researchers. So you get a result that is something like, you know, taking data that starts looking something like this, which is not in any way conceptually intractable, but is really, really annoying to work with. You have to convert the time out of these weird milliseconds from epoch format, not Unix epoch either, special mission epoch. Average and differential things deal with this bit flip, set of bit flip errors, the jaggedy things, and the red arc, all of these spikes, and turning it into, you know, like a nice temperature by time curve in standard units that you can rapidly ingest and actually use without spending 15 or 20 hours fiddling around with units. So we end up with essentially 3 different data flavors for different use cases. One that we call the clean set, which uses the exact same data format of the Lamont data as ingested by the NSSDC, which is this sort of IBM 1130 equivalent fixed width number format, but adds this column for corrected temperature difference, a bit mask of flags for missing values, things of that nature. Something we call a split set, which goes ahead and converts the time values, substitutes our temperature differences, explicitly computes temperature values, sticks all the data into a single time record. And then finally the depth set, which is like full on maximum ease of use, temperature by time by depth at each site. So that's the basic structure of what we produced. And then our final priority that I wanted to discuss was clarity. And by clarity here, I mean partly just improved high-level documentation, but I also mean an emphasis on software as documentation. So clear code comments, complete traceability and reversibility of our work for further error correction, extensibility, rapid ingestion in other formats, and so on. Okay, that's all I'm going to talk about our design priorities. And I want to switch over to talking a little bit about my experiences learning and working with PDS4, the archival process and standard, along with some observations, tips, tricks that might be briefly useful. This is not a complete tutorial by any means. Okay. So the most general observation I want to make about PDS4 archival is that it ends up looking a lot like a document prep, document cleaning, data cleaning task that is much more common in biz dev than in science. And it's a little bit of a gear shift. I'll note that everything I'm about to say here, my process and recommendations might look different if I'd chosen to approach this using a dedicated XML editor like Oxygen. I decided to forgo that particular set of complexities and just use my text editor of choice with the Pds Validate tool as an in-step verification tool, but there's a whole other kind of tool chain that you might explore instead. That's total level of effort. If you are getting off the ground with PDS4, like have not worked with the PDS4 format previously, I mean, in terms of actually like making labels, I recommend that you expect to spend 2 to 3 weeks of focused effort on getting up to speed and archiving a data set of this size, which is not, I should emphasize, particularly large or complicated. And I think it's important to note that archival time, like in terms of investigator hours, labor hours, scales more quickly with complexity or variation than with total archive size number of products. So every type of product you add to your archive, like a new category of image, a new type of table, et cetera, is a significant addition in effort. But adding additional products within those categories is a much smaller addition in effort. There are some things that do scale in terms of effort with number of files, and those are things that vary per file. So recording line numbers, date ranges, data sources, file sizes, et cetera. Some of this could be quite easily automated, writing out file sizes, line numbers, and so on. I didn't consider the automation effort quite worth it for a data set of this size. It was just on the line, but it most likely would be for a slightly larger set in terms of number of products. Okay, essential documents. So it is important to understand that there are 3 mutually supporting references, like separate documents, you need at hand to fully investigate and follow PDS4 standards. Those are the Planetin. I'm going to pop up a browser here with them open. Yeah, great. And so those are the PDS information model, the PDS standards reference, and the data provider's handbook. basically, the information model describes the valid structure of all label types. The standards reference describes overall bundle and collection structure along with the valid content of both labels and products. And the data provider's handbook provides some contextual information that's necessary to fully understand both the model and reference. I should also add here that the label making processes past quite simple examples are not officially documented anywhere. So in addition to these 3 documents, it's important to have a broad selection of existing PDS4 labels from structurally similar products in so much as you can find them. And then secondarily to that, I strongly recommend taking a look at the small bodies node PDS4 wiki, which is not fully complete because it's not official documentation. It's a community sourced wiki. Some of it's a little out of date. Some of it contains rules that are specifically applicable to SBN bundles and topics, but it's a really, really useful resource. Okay. Briefly discussing a few gotchas I encountered in the archival process. One of these gotchas is the concept of logical identifier as a whole, and especially lots of entities that are not data products, bodies, instruments, missions, etc., have existing logical identifiers. When referencing any entity that has a pre-existing LID, you need to use that LID. Note that some abstract or collective entities like dust also have LIDs. Now, unfortunately, to my knowledge, there's not a comprehensive index to logical identifiers. Using the top level PDS keyword search is sometimes, but not always, effective. Like if you want to know the LID for the moon, great, we have pretty easily found the LID of the moon. That's wonderful. But you may need to do some digging in other PDS archive to find LIDs for more obscure bodies, targets, instruments, or to verify that they haven't yet been assigned. XML as such contains gotchas. So I personally, and I think this is probably the case for a lot of other scientific programmers, had worked very little with XML before. One important thing to note is that unlike PDS3, tag order matters. This will be a theme if you've worked a lot with PDS3. PDS4 is a much more finicky format. And this tag order matters thing is also unlike JSON and many other complex common markup languages you might have used. This got me into trouble a couple of times, and it's really annoying to fix in an automated fashion. The most complete way to look at required tag order is to go into the information model and drill down through hyperlinks. So if you want to look at, for instance, what the file description in an observational product label should look like, we can drill down through file area observational into maybe a table itself. And here we see that it must have a defined record delimiter, may or may not have local identifier, MD5 checksum, name, description, number of data offset, number of records, all in that order. Also note that certain values, yes? Oh, something else, okay. Certain non-optional values have only one legal entry but are still non-optional. For example, record delimiter may only be carriage return line feed, but must still be specified. And I'll talk a little bit more about new lines in a second. Other things to remember with XML, indentation doesn't matter, and line breaks don't matter. Okay. A note about archiving software. The PDS does not archive software. However, you can include software as documentation in a document collection if you clearly label it as documentation and not as working software, and claim that a separate repository, not the PDS, is the actual archival location. The NASA Planetary Science GitHub account is one possibility. And this is really important if, like us, you see software as a crucial part of the documentation of your output data. Okay. A couple of notes on tools I found helpful. I talked about line endings a moment ago. PDS4 mandates CRLF, carriage return line feed endings, which are the Windows standard. These are really annoying to fix in most text editors and will be a consistent problem if you are producing things on Mac or a Unix. And it's also moderately annoying, at least from Python, to output tables with your chosen line endings. In particular, Pandas has deficiencies in formatting fixed width files that include the inability to select line endings other than OS default. I could go on about that for a while, but I will restrain myself. However, bulk modifying all line endings in a batch of files is really easily done with a utility called Unix to DOS, which is an ancient, tiny gem of a program that does its adorable little job incredibly well. It's readily available for most Unix distros and on Mac OS through Homebrew. I highly recommend it. I'm a big fan of automated code formatters and beautifiers. I'm going to recommend another old utility that's simple and to the point for XML, and that is XML format, which is great for just adding regular line breaks, a sensible indentation model, and in general, making your XML immediately readable to yourself and others. There is a much more sophisticated ecosystem of XML shell tools, should you care to explore them. The most popular ones are XML lint and XML starlet. I have not experimented much with them and cannot say much about them. Other tools. It is my opinion that the classic Unix text processing utilities are some of your best friends for a whole bunch of label making applications, and especially label correction or label modifying applications. So I'm talking about like sed, find, awk, grep. I'm not a guru with any of these. Nevertheless, you can do in a line or two with these what would take multiple library imports, several lines, etc. in Python. Perl, of course, would be highly suited for that task, but if you're great at Perl, you don't need my advice with, probably anything. I'm going to share like maybe a slightly embarrassing list of, I'll open it here. Yeah. So like, here are some teensy little one-liners that I use to fix a bunch of problems in some of my labels. And it is incredibly rapid and efficient. Like, oops. It turns out that the logical identifier for this is not the logical identifier I thought it was. Rapidly change all of this in a directory with a one-line set instruction. Oops, I should have specified the months explicitly. Rapidly with a one-line find instruction, change that in everything in my entire bundle. So, strongly recommend, if you're not already a fan, exploring these really simple Unix shell utilities to take a lot of load off of your back. And then finally, of course, I need to mention the central most important tool, which is the Pds Validate Tool. So there are things about the Validate tool that are a little clunky, and it needs to be pointed at a Java runtime environment, which can be finicky, but it is extremely powerful. So not only does it perform XML scheme verification like something like Oxygen could, it also verifies the relations between all members of a collection and then collection to bundle. And it even verifies the relationships between observational product labels and the content of those data products. So it will verify that the data in the fields of a table is structured like the label claims that it's structured. And also note that you don't have to use it for this enormous batch correction. You can also use it as a rapid one-shot single file tool for quick label verification and validation in the same way that you might use something like Oxygen, which is one of the reasons that I chose not to use Oxygen. And that's super powerful and something that you should bring into your workflow ASAP if you're building a PDS4 archive. And that's the end of my sort of planned list of tips, tricks, and observations about my PDS4 experiences. And if anyone has any quick questions about either our archival decisions or the structure or content of our data sets or anything I said about PDS4, I'm happy to take a few questions.
We'll give everyone just a second to type.
Can we ask questions just by voice?
Sure, go ahead. I just didn't want everyone to do it at once, but if it's just you.
I'm Matt Tiscarino at SETI Institute. I'm also with the PDS Ring Moon Systems node.
Wonderful.
And thank you for this very helpful tutorial. It's really helpful to understand as much as possible everyone's point of view as we are working to do all of these archiving tasks. The most important thing that I noticed that you did not mention at all is what node were you working with?
Oh, Geo, sorry, yeah.
How were they available to help you with all of these tasks?
We did not directly interface with Geo until after we had prepared the bundle as a whole. They were aware that we were working with it, but we took on archival practices ourselves.
Okay, well, I can't speak for Geo, but I know that, I mean, this obviously is going to be taken as being relevant to a lot of people who are ROSA's grantees and are thinking about archiving with PDS. And in general, I don't think we are expecting data providers to spend several weeks becoming familiar with the information model, maybe because you have a bigger data set and maybe you're more of a mission level data provider. I don't know, maybe that's what you need to do. But for the most part of the reason we have science staff at all the PDS nodes is so that we can be very freely available to answer questions and help walk people through the process, even help them write the labels, in some cases even be doing the bulk of that label writing work for you. So just want to let you know that your node staff is available. We want you to ask questions. We want to help you through the process.
Great. Thank you. I'm glad that that staff is available for many purposes.
In fairness to Geo, we didn't ask them for help because we kind of wanted to know how to do it.
Yeah.
Okay. Thank you, Michael.